So welcome back, everyone. Thanks for showing up today, those of you who made it. I know you're anxious to get started with your reading week so you can go do whatever it is you can do these days on a reading week. Probably not travel too far. So there's a few minutes before class and lots of latency on this connection. So I'll ask you if you have any questions. And at the same time, I will add to something that you may have heard or not. Something I said on the Discord server about assignment 3 being potentially very time consuming. And the point of me saying that was to convince you guys to start early. And the reason for that is that it's working with pointer-based data structures, and they're tricky. Bugs can be subtle and difficult to find. Java helps a lot with that. But also, it works with some fairly high-level concepts. And there will be times, if you end up debugging this, or if you get stuck with your debugging, there'll be times when the best thing to do is to walk away from the computer and think about what you've done and what's maybe going wrong with your implementation, and come back to it fresh that way. And if you don't start early and you're doing this at the last minute, then you won't have that option of just walking away from the computer and coming back later with a fresh mind. And in my experience, when you're up against a time limit and there's something really tricky like this, it just tends not to work out. So you get panicky, you make random changes, things get worse. Maybe you even forgot to save old working versions, and things get really bad. So the point is just that. Start early. Doesn't mean you have to work continuously from now until the assignment is due, but go read the assignment now. Think about how you would solve it, how you're going to approach it. Have a good plan before you even sit down and start programming. And then, if you're programming for a while and you get stuck and you need to rethink your solution, walk away from the computer and think about it. Give yourself the time to do that properly. Okay, so question from the previous class: the random treep is a treep with random priorities. Does the priority have to be a real number? Can it be a letter? So in fact, it can't actually be a real number because computers can't represent real numbers exactly. So it's going to be, it could be a float or it could be an int, but in any case, it's going to be a string of random bits. And so whatever it is, it should be a large enough string of random bits that makes it unlikely that two different nodes will get the same priority, or that there should not be a lot of nodes that have the same priority. So question was, could it be a letter? Well, if you're only using, for instance, lowercase English letters, then there's only 26 letters. And if you create then a treep with 1,000,000 nodes, well, that means some letter is going to occur 1,000,000 divided by 26 times. In fact, there'll be lots of repeated priorities, and your treep will have to do a lot of tie breaking when it's doing stuff. And in general, when you implement tie breaking, it's typically by favoring one side or the other, the left side or the right side, and that can often work against you. So always favoring one side or the other can lead to really long paths. Like if all the nodes with priority A, those are the ones that would be at the root. If all of those form a big long path to the right, that's not good. So the priorities can be anything as long as you can compare them, and as long as there's enough of them that they don't collide too much. Yes, what does balanced mean in terms of binary search tree? So typically balanced, it's a sort of really generic term, and then people use qualifiers like weighted or weight balanced or height balanced. But the generic, as a generic term, if you say it's a balanced binary search tree, what you typically mean is that if the tree stores n elements, then its height is some constant times log n. Okay. So then the length of any search path is also at most some constant times log n. Trees have this property. We didn't prove it explicitly. We proved that for any particular search path, its expected length is, we didn't even prove that, we just stated it. Its expected length is a constant times log n. But in fact, trees have it for the whole tree with high probability. But in general, balanced means logarithmic height. Yeah, I mean, if two nodes in a tree have the same priority, you then have to look really carefully at the code that you're using for insertion and deletion to say, well, what does it do? There's usually a specific while loop that says, while the priority of me is less than the priority of my parent, do a rotation. Well, it depends now whether that says less than or equal to, exactly what happens in those two cases. And similarly, when you're deleting, you look at the priority of the two children of the node you're trying to delete, and you take the smaller priority and rotate it so that it becomes it replaces you. But if those two children have the same priority, that probably means your code has some bias in it, that it's always going to take the right child in that case, and that can be bad. Okay. So today I want to talk about, the lesson today is about scapegoat trees, which is another kind of balanced binary search tree. So it's a search tree that will guarantee that the height is logarithmic in the number of nodes in the tree. And they're sort of motivated by this example that I've drawn on the board here. And there's questions, and maybe you read them while I was blabbing about other stuff. So the question is this a good binary search tree, or is this a bad binary search tree? And most people look at this and say, well, this doesn't look great, because, and in fact, if you think of, if you've worked with, you've seen a bit of data structures before, and in particular balanced binary search trees before, you would say, whoa, this doesn't really look balanced at all, because at the root has a left subtree that has 15 nodes in it, and the root has a right subtree that has 0 nodes in it. So certainly if we think of balanced as being in terms of a scale, a weight somehow, then this doesn't look very balanced here at all, because all the weight is on one side. So that's not good. So that's usually what you call the definition of weight balance says something about the number of nodes in the left and right subtree. So this is terrible under that measure. Another version of balanced is what they call height balanced, and that also fails this thing. So if I look at this node, it has a left subtree and it has an empty right subtree. So the height of the left subtree is 1, 2, 3, and the height of the right subtree, it's an empty subtree. I don't know if you remember this, but when we had defined the height of trees, the only thing that made sense for empty subtrees was to define the height as -1. So on one side it has a tree of height 3, and on the other side it has a tree of height -1. That also doesn't seem very balanced. But there's a third way of looking at it, which is a little bit like this picture here, is just to look at the height of the whole tree. Don't worry about any particular node, because really here the only problem seems to be at the root. Every other node looks pretty good. In fact, every other node looks perfect. It's just the root. And if you look at the height of the whole tree, the height here is 4. And you might think, well, could I do better than that? Could I make a tree that has lower height than that has all this data in it? And there I think it's quick to see that the answer is no, actually. There are 16 values in this tree, this binary search tree, and it's impossible to have a binary search tree with 16 nodes whose height is smaller than 4. If you don't believe me, just look here on this side. Here's the biggest binary search tree of height 3 that you can have, right? It's completely full, and it doesn't have 16 values in it. It only has 15 in it. So it doesn't matter what I tried to do to make this tree better, this number is not going to get any smaller. The height will not get any smaller. And, well, height is everything, right? Because no search path is longer than the height, so under that measure, this is the best search tree you could have. Why is the height always 1 less than the number of levels? The height is just defined that way. The height of a tree is equal to the maximum depth of any node. And what's the depth of a node? The depth of a node U is equal to the distance from U to the root. Okay. So why is the height always 1 less than the number of levels? The height is just by definition that's what it is, because the depth of the root is 0. The root is distance 0 from itself. All the nodes at this level are distance 1 from the root. All the nodes at this level are distance 2 from the root. These ones are distance 3 from the root, and these ones are distance 4 from the root. So it's just a definition. And that's because it kind of makes sense to define depth in terms of distance, and then everything else works out. That's where height comes from. And why I say that the root has depth 0? Well, because we like to count starting at 0 in computer science, let's say. No, so remember, so you said the depth on the right, or the height on the right, is -1. So I said the height of the right subtree, which is empty, is -1. Why is that? Well, because the height of this tree, which has only one node, so it actually has a node of depth 0, its height is 0, because the maximum depth of any node is 0. So that means the empty tree shouldn't have the same height as the tree with a node in it. So the only thing that makes sense is to define the height of the empty tree as -1. And then if you do that, all things like recursively defining the height in terms of being the height of the two subtrees plus 1, the max height of the two subtrees plus 1, all of those things work out. If you define the height of the empty tree also as being 0, then you have a problem, right? Because this is supposed to be a tree of height 0, and it has, but it's the parent of two empty trees. If those each have height 0, well, why doesn't it have height 1? So let's, but don't get too hung up on that. Okay. All right, so these things called scapegoat trees, they focus on what they think is important, which is just the height of the tree. That's all they care about. They want to make sure that the height of the tree is not too big. Okay. So, here's what scapegoat trees do, and they do this in a kind of a brutal way. They don't try and, unlike trees, for example, they don't try and finesse things using gentle rotations to make things move to the root. They don't keep really careful balancing information. They just wait until something goes wrong, and then they just come in and clobber part of the tree, destroy a whole part of the tree, rebuild it nicely. So nothing, there's no finesse in scapegoat trees. So what does a scapegoat tree have? Well, it'll have a binary tree. It'll have a counter n, and as usual, n equals the number of nodes in the tree. It has another counter q, and q, I'll just say it's a high water mark. We'll discuss what that means later, but the main thing about q is that it's bigger than or equal to n, and actually it's going to be smaller than or equal to 2n. Okay? So q is kind of like an estimate of the number of nodes in the tree. It's never an underestimate, so it's always bigger than or equal to the number of nodes in the tree. But it's never a huge overestimate. It's never more than twice the number of nodes. So you wonder, why don't we just keep track? We know exactly the number of nodes. Why do we need q? That'll become clearer as we discuss it. Okay. And what this thing will maintain is that the height of the tree is always going to be less than or equal to log base 3/2 of q. So I was saying a balanced tree, the definition is it's some constant, its height is some constant times log n. So this relaxes that a little bit and says, well, it should be some constant times log of q, but that's not such a big relaxation because q is not much bigger than n anyway. Okay. In fact, we can immediately plug this in and say, well, that q is not more than 2n, so that's at most log base 3/2 of 2n. And if you remember how logarithms work, the log of a times b is equal to the log of a plus the log of b, which means that the log of 2n is equal to the log of n plus the log of 2. And log of 2 is a constant. So really, this thing is a constant times log n. And if you're uncomfortable with this, what is this 3/2 in the what does this mean? The base 3/2, log base 3/2. Well, log base 10 of a number is just the number of times you have to divide the number by 10 until it becomes less than or equal to 1. Log base 2 of a number is the number of times you have to divide the number by 2 until it becomes less than or equal to 1. And so log base 3/2 of a number is the number of times you have to divide the number by 3/2 or multiply by 2/3 until it's less than or equal to 1. Okay? So let's just make a note of that. It says number of times to multiply n by 2/3 before it's less than 1. Okay. So really, it's this solution to 2/3 to the I times n equals 1. Okay. That's the way to think of it. How many times do I have to multiply by 2/3, or if you like, divide by 3/2? And of course, this is it's the way I like to think of logarithms, and it's probably the way you should think of them. Of course, this is not always it's not always an integer that you get here, and then to understand that, you have to kind of you have to talk about the exponential function. But the useful sort of working definition is it's the number of times I have to divide by something before it's less than or equal to 1. That gets you within 1 of the actual correct value of the logarithm. Okay. All right, so we're going to guarantee this. And so let me just leave this part up here. This is less than or equal to log base of 3/2 of n plus a constant. All right, this is a constant that is bigger than 1 but smaller than 2, because 2/3 squared is 4/9, which is less than 1/2. So if I multiply 2 by 4/9, I get something less than 1. So this thing here is less than 2. In fact, for precision, let's just put that there, 2. All right. So those are the rules of scapegoat trees. You got to keep track of n. You got to keep this number q that follows these rules. It's between n and 2n. And the height of the tree is always going to be, at most, log base 3/2 of q. So scapegoat tree is going to guarantee that after every operation, all of these things are true. Okay. All right, and so what are the binary tree operations? The 3 important ones, the ones that really everything else is based on, are add, remove, and find. So add, remove, and find. And one of those is easy, because in binary search trees, find always works the same way, at least in the kinds of binary search trees we'll study. It starts at the root, and then searches, does comparisons, follows the search path for the value x until it either finds the node containing x or it leaves the tree, in which case it concludes that x is not in the is not stored in the tree. And how long does that take? Well, it takes time proportional to whatever the length of the search path was for x. So that's just the depth of the node that has x in it. But remember, the height is the maximum depth of any node. And so, so the length of the search path is never more than the height, which means it's never more than this, or this if you prefer to digest this. Okay? So it's never more than log base 3/2 of n. So find follows a search path of length at most log base 3/2 of n plus 2, and so that means that find runs in O of log n time. I don't even know yet how add and remove work, but if this is the definition of a scapegoat tree, then definitely find will run in O of log n time. Now we just need to see how add and remove work. And we'll start with remove. So here's what remove x looks like. And this is useful because it illustrates the classic algorithm for removing something for a binary, from a binary search tree. I'd like to do a good example, so maybe Here's a good example. So I call remove x. Remove x searches in the tree until it finds x. So maybe it finds x, for instance, down here at a leaf. And we saw already when we studied trees that that's really easy. We just delete it, right? I mean, x, this node has a pointer to its parent, which means we can go to the parent and then change its right pointer, in this case, to be null, and then x is gone from the tree. All right. So that's kind of an easy thing to do. Let me draw a few more nodes here. What happens if I find x here, for example? This node. So this is a node that does not have a, well, it has one child, so it's not a leaf. It doesn't have two children, it has one child. So what should I do in that case? Well, it turns out that that's also easy, because I want this node gone, but if I just really cut all the links to it, then I lose a piece of my tree here. But I only lose one piece of my tree, because x didn't have two children, it only had one child. That's why there's only one piece hanging around here. And since I just detached from my parent, there's a very natural place for me to reattach. Now, convince yourself, wait a minute, is that still going to be a binary search tree? Yes, it will. And why? Well, x was the right child of its parent. And remember, the rule for binary search trees is that everything in the right subtree is bigger than the parent. So I get rid of x, and I replace it with something else. It's not equal to x, it's equal to this thing. But still, I know that it's bigger than whatever was here at the parent. And so that means whatever's here at the parent, everything in the right subtree is still bigger than it. It was bigger than it before, it's bigger than it afterwards. So deleting a node with only one child is easy. There. All right, so then let's look at another example, probably the hardest one. So we can know how to delete a leaf that has no children. We know how to delete a node that has only one child. And we know how to, or we don't know how to do, is delete a node that has two children. And that's problematic. So here it looks problematic because it's the root, but it would also be problematic even if this is the node I wanted to delete, because if all I do is cut it out, then I have two subtrees that are dangling off of here and only one place to attach to, so I can't attach them both there, and so that is not going to work. And instead, you do something clever. Let me put numbers on here so that you can see why this works. So there it is, there's that same binary tree, but now with the numbers attached to the nodes so that you get a binary search tree. And I want to delete 4. 4 has two children, so I need to deal with that somehow. And the trick is you won't actually delete this node. What you'll just do is take some other value and put it there, or replace it with some node if you like. Okay. So here's 4 at the root. I want 4 to go away, and I want to replace it with something else. And of course, it has to be a binary tree when I'm done. And so that really means there's only 2 options for what I can use to replace it. So remember, being a binary search tree means that whatever's at the root has to be bigger than everything in the left subtree, and it has to be smaller than everything in the right subtree. So that means whatever I replace this with, it could be the largest thing in the left subtree, 3 for instance, or it could be the smallest thing in the right subtree, 5 for instance, but nothing else is really going to work because if I take something else, then I'm going to have a problem either with having something smaller in the left subtree or something smaller in the right subtree. And you get to choose. It's a sort of implementation detail whether you decide to take something from the left subtree or whether you decide to take something from the right subtree. It doesn't really matter because you know they're both not empty. So in either place there's something to take. So the sort of rule I like to use for, I don't know why, maybe because I'm right-handed, is to always take it from the right subtree. And how do you find that thing in the right subtree, the thing that is the smallest thing in the right subtree? It's actually really easy to find. You take a step into the right subtree, and that takes you to a node. You know there's a node there because this thing has 2 children. And now, as long as this node has a left child, you go to its left child. Now I'm still at a node that still has a left child. I go to its left child. Now this node doesn't have a left child. I can't go to its left child. And I claim that that's always going to be the smallest thing in this tree. Why is that? Well, it just comes from the definition of binary search trees, right? If I started at the root and I only go left, well, that means I'm going to always something that's smaller than what's at the root. So over on the left is everything smaller than the root. And then I do that again. So over on the left is everything smaller than the root. And that means that if I'm at the left, there's nothing smaller than the root. But the way I got there is by going into a subtree that always had everything smaller at the root. So this must be the smallest thing. So the root of this subtree is the smallest thing in this subtree. Okay, so so there you go. You have the node with 2 children whose value you want to remove. You go into its right subtree. You go left, left, left as many times as it takes until you can't go left anymore. And that's the value you're going to take. So you take that 5, copy it up into there. And if you don't like copying values, you can just change the pointers at this node. And now this node here has no value in it anymore because you moved it up here. So that means you've still got an extra node, but now it's an easy case because this node has no left child, which means it has either no children or only 1, but we already know how to do it when it has no children, when it's a leaf, and we already know how to take care of it when it has only 1. So in this case it has 1. We've just applied the technique for 1, which is just to splice it right out. Okay. So that's what remove looks like. And in a scapegoat tree, that's what it looks like. So I'll just say you use basic binary search tree remove. So that's what I just described, the 3 cases, whether it has 2 children, 1 child, or it's a leaf. You do that, and well, you're not done because remember there's these things here. There's an n that you need to decrement because n just went down. So you do that. And now you're still not done because remember there's this value q here. And q has to satisfy these two conditions. Q has to be bigger than or equal to n. So if it was bigger than or equal to n before, and I make n smaller, q is still bigger than or equal to n. That's not a problem at all. But q also has to be less than or equal to 2n. And if I make n smaller, so maybe q was actually equal to 2n before, and now I make n smaller, and now q is not less than or equal to 2n anymore. It's bigger than 2n. So in that case, I need to do something. So if q is bigger than 2n, then rebuild the root. And what is this rebuild operation? Well, it does what you might suspect. It takes the whole tree, so the whole thing from the root, and rebuilds it into the best binary search tree that it could possibly make. So it completely destroys it and rebuilds it perfectly. So if it was a, so what does that mean? What does it look like when it rebuilds it perfectly? Well, that means that it has almost exactly the same number of nodes on the left side as it does on the right side. The only difference possibly is it's off by 1. If the total number of nodes is even, then once you take away the root, it's odd. Then you get the ceiling of half here and the floor of half here, or vice versa. So there could be a difference of 1, but otherwise it does it perfectly. And it does that recursively inside each subtree as well. So at the next level, these two things are exactly the same size. And so those two are equal. And that's with, I put a little tilde there to mean plus or minus 1, because if there's an odd number of things, then you can't make them exactly equal. And so on recursively, all the way down. Okay. All right. So when you do a rebuild like that, if there's n nodes in your tree, then the height will be log base 2 of n plus 1. And you can check that yourself. So why the n plus 1? Well, it's really because if your tree is as perfect as it can be, it has 1 node at level 0, 2 nodes at level 1, 2 nodes at level 1, 4 nodes at level 2, 8 nodes at level 3, and so on. So it's 1 plus 2 plus 4 plus 8 plus 16. And if you add all of that up, you see that it's a power 2 to the height minus 1. 1 plus 2 is 3. That's 4 minus 1. 1 plus 2 plus 3 is 7. That's 8 minus 1. 1 plus 2 plus 3 plus, 1 plus 2 plus 4 plus 8 is 15. That's 16 minus 1. So when you do this rebuild operation, a nice looking tree comes out. Okay. And the main thing I want us to remember about rebuild after rebuild, for each node u in the rebuilt tree, the size of u dot left minus the size of u dot right is less than or equal to 1. So right after I rebuild, those two trees have almost exactly the same size, as good as can be. Same situation we had with the dual array deck with the front and back after a rebuild. After a rebuild, they have almost exactly the same size. All right. So that's the remove operation. And let me do the add operation, maybe on the same example, although I'm pretty sure that I'll get the numbers wrong because I cannot do, in my head, I cannot take log base 3 halves of some number in my head. That's not really critical. Okay, so back to this thing having 5 and this thing having 4. So we have n here. N is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So n is 14 in this picture. And q can be anything between 14 and 28, right? The only condition on q is that it's not more than 2 times n. So I don't know, q is going to be something. And let's pretend for a moment, 1, 2, 3, 4, 5. I won't tell you what q is, but let's, oh, yeah, no, that's 7, 6, 8. Let's pretend for a second that q is, I don't know, 20 is something, but that log base 3 halves of q is equal to 5.12. I don't know. I can't solve that, and probably this definitely does not have an integer solution for q, but q is some number, I don't know, maybe it's 26, and that gives you some answer like this. So if I look at the height of this tree, so why did I pick 5.12 for being the log of q? If I look at the height of this tree, it's 1, 2, 3, 4, 5. Now q is supposed to, or log of q, that's why I'm interested in the log base 3 halves of q, it's supposed to be bigger than the height of the tree, which is why I imagined some number so that the log base 3 halves of q was 5.12. And you can think of this, and this is why it's good to think of q as a high watermark. This is what q looks like. q is somehow drawing a line that says the height is not allowed to go below this mark. Right now, the height is up here at 5. And it's not supposed to go below log base 3 halves of q, and that's whatever, 5.12. So right now this tree is okay, according to this rule. Yes, you're right. So after you rebuild, you say q is equal to n. That's a good point. Eugen said, don't we have to do something after rebuilding? In this case, we do. After we rebuild the root, we set q equal to n. And that's certainly going to be okay because we just rebuilt. We have a tree whose height is a log base 2 of n plus 1, and you can check that a log base of 3 halves of n, at least actually for all the n's we're interested in, the height of that is log base 3 halves of n is bigger than log base 2 of n plus 1. So that operation resets Q, and now, so how did you get to this state? You got to this state because Q got much bigger than n, but as soon as you get to it, you set Q back so that it's exactly equal to n. Good. Thank you for asking that. Okay. So now I want to add to this tree. So I want to add some value x. And maybe I want to add 3.5. So we use the normal trivial algorithm for adding to a binary search tree. Start at the root and follow the search path until we fall out of the tree, and then we attach the thing. So if I want to add 3.5, then at the root I go left because 3.5 is smaller than 4, but it's bigger than 2, it's bigger than 3, and at this point I fall out of the tree, and that's where I would add this thing. And at the same time, I keep track of how many steps that I took so that I know the depth of this new node that I added. So 1, 2, 3. So this node was added at depth 3. And, well, that's good. 3 is not bigger than 5.12, so I know that I didn't increase the height of the tree by more than Q here. Okay. So I didn't increase the height of the tree so that it's it's bigger than log base 3 halves of Q. So that's good. In that case, that's all I do. Attach it there. And similarly, if I want to attach maybe 10.5, then I'll follow the search path for 10.5. Takes me out to here. I attach 10.5. On the way down, I was counting how many steps I took. 1, 2, 3, 4. 4 is less than log base 3 halves of Q, so still okay. No need to do anything. So let's start to write that down. So we add x using the usual algorithm. Okay, and we have to, we just added x, so we better do an n++. So when we add something, the number of nodes has increased, so we have to increment that. But we also have to make sure that Q never gets smaller than n. And so since we just increased n, we should probably increase Q as well. Let's do that. Then as long as Q was bigger than n before, it's still going to be bigger than n after. And 2n, it was bigger than or equal to Q before. We just increased the value of n, so 2n went up by 2, and Q only went up by 1, so Q is still smaller than 2n. In fact, if it was equal to, now it's actually smaller. So that part's good. We didn't break anything there. But I said we've been checking if the depth of the new node is bigger than a log base 3 halves of Q, then we have to do something. Then we want to find a scapegoat. And rebuild U. Okay. All right, so I'll now explain what it means to find a scapegoat and what it means to, well, we've seen what it means to rebuild, but in this point, we're going to find a scapegoat, a node, U. We're going to blame all of our problems on you. That's what it means to be a scapegoat. It means someone's blaming you for everything. And then we're going to rebuild just the subtree rooted at U. So we won't necessarily rebuild the whole tree, just the subtree rooted at the scapegoat. Okay. So what does a scapegoat look like? So let's review what happened here. We just added a new node X. It went below our high water mark. To get to that node, we followed a path from the root to X, and the path was too long. That's how we know it went to below the high water mark. And now what we're going to do is walk up this path until we find what's called a scapegoat. And what does a scapegoat look like? Well, a scapegoat is a node that looks like this. Well, I'll tell you. Here's a picture of a scapegoat, a sort of idealized picture. Looks like this guy. So one of its subtrees is much bigger than the other. And what does that mean exactly? It means that one of its subtrees has size bigger than 2/3 times, so if this is U, the subtree here has size bigger than 2/3 the size of U. Okay? So that's what it means to be a scapegoat. I look at the size of U, I look at the size of the two subtrees, and if one of them is bigger than 2/3 the size of U, then this is a scapegoat. And this seems like a reasonable candidate to rebuild because, because it's so unbalanced, right? It's got not very much here, and it has lots here. So that looks like the right thing to rebuild. And U will be one of the nodes along this path. So that really means, if I think about the picture here, there was a little subtree over here, and then a subtree over here. Now, beforehand, this subtree was not below the high water mark. It was not below this line. So all of its nodes were above this line. But I just added one annoying node that put it below this line. So that's one thing. And now the other thing to notice about this is that U is not, it's not perfectly balanced, right? Because more than 2/3 of its nodes are on this side. So that means it's not perfectly balanced. And that means that there's room over here to add one node without increasing the height. There's some space in here that I could add one node without increasing the height. Why is that useful? Well, that's useful because, right, here's that one annoying node X. So when I rebuild, I don't know exactly what the whole picture is going to look like, but I do know that it's going to take me back above this line. Okay. So this is rebuild. How do I know it's going to take me back above this line? Well, because when I rebuild, I get the best binary search tree that I can have, so meaning the least height. And I know that with this many nodes, I could get one whose height is above the blue line, because if I didn't care about being a binary search tree, I could have just attached this node over here. Now I still care about being a binary search tree, but I'm rebuilding the whole thing into the best tree that it can be, so definitely this node and every other node is going to end up back above the blue line. So, so that means if I find the scapegoat and I rebuild, then I will have solved the problem. So in this picture, this thing is going to get rebuilt into something more balanced. X is going to be in this tree. U will be somewhere in this tree, but it won't be the root anymore. It was a terrible root, right? Some other node will be the root, but the whole thing will be back up above this blue line. So once this is done, I can return safely, and I know now that the height of the tree is still less than log base 3/2 of q. And in this case, I don't change the value of q. I leave it the way it was, even though I rebuilt something. Okay, all right, so now maybe the only thing that might concern you is, do we rebuild the whole tree or just the subtree with root u? Just the subtree with root u, right? So I found u here, that's the part I rebuilt. The rest of the stuff, the whole rest of the tree, there's all kinds of other stuff hanging off here. I didn't touch any of that. Just the scapegoat. So now you might say, okay, how do I know that I'll find a scapegoat? How can I be sure to find a scapegoat? There's a problem if I don't find one. And how can I be sure to find a scapegoat? Well, that's not too hard to show. Look at the root here. So the root is the root of a subtree with n nodes. So if it's not a scapegoat, so remember there's this whole path from the root down to x. If n is not a scapegoat, that means, so I need to take a step down towards x and into some subtree, the one that contains x, but the root's not a scapegoat, so that means that this whole subtree has size less than or equal to 2/3 of n. That's the size of the whole tree is n, right? And it's not a scapegoat, so this subtree is not bigger than 2/3 the size of n. This subtree is not bigger than 2/3 the size of n. But in particular, the step that I just took takes me into something whose size is less than 2/3 the size of n. Okay, so that's what happens if the root is not a scapegoat. What about this one? What if it's not a scapegoat? Well, this path continues down to x. Maybe it goes down to here. So let me just write this down. Less than or equal to 2/3 n. So if this guy is not a scapegoat, then when I walk into his right subtree, or his subtree containing x, that is also going to be less than or equal to 2/3 the size of his total subtree, which is at most 2/3 the size of n. So that means this thing here is less than or equal to 2/3 squared the size of n, this subtree. Now if that's not a scapegoat, then at the next step I will walk into a tree whose size is less than or equal to 2/3 cubed times the size of n. Now, how many times can I do this? Well, it's gone now, but it was there for quite a while. What is the definition of log base 3 halves? It's the number of times you can multiply by 2/3 before you get something less than or equal to 1. So if I keep walking along here and I'm never seeing a scapegoat, then the furthest I can walk down here without seeing a scapegoat is at most log base 3 halves of n. But n is less than or equal to q, so that's also less than or equal to log base 3 halves of q. So if I walk down this whole path and never see a scapegoat, that means I didn't walk below the low watermark, the blue watermark. Or if you like, if I inserted and I ended up below the blue watermark, that means that there must have been a scapegoat along this path. There was somebody along this path who didn't do their job of reducing the size of the subtree by at least 2/3. That's the one you blame, that's the one you rebuild. Okay. All right, so that's how the structure works. And now it's time to analyze it. Okay. And let's see what we've got. We have find, we already know that takes log n time because the height of the tree is log base 3 halves of n plus 2 at most. Remove, well, it kind of has two parts. It has this thing where we have to do the basic binary search tree remove, and that's just following a search path, and then maybe after we find it we have to keep going down a little bit, but that's not more than the height of the tree, that's only log n. Then this stuff is easy, that's just constant time. This test is easy, it's constant time, but this is a whopper. If we have to rebuild, then that takes linear time. I mean, we have to go through, destroy the entire tree, and then put it back together in a perfect shape. So it's not hard to do that in O of n time because, well, the dumbest thing you can do is traverse the tree. We've seen how to traverse the tree and get all the nodes out in sorted order through that traversal, and then you can rebuild by, you know, put all those nodes in an array, and then you go right to the middle of that array, and you make that thing the root, and then you recursively build using the first half of the array and the second half of the array. So that rebuilds the tree perfectly balanced in order and time. Okay. But that's not good. That's slow. So now you may guess that, okay, this is not going to be an easy analysis. This is something where we're going to have to use amortized analysis again, because now we see that some of the remove operations, they won't run in log n time. They'll take a huge amount of time, linear time. And now let's look at adding. And there, it's the same story. This part is easy. Adding using the usual algorithm is just following a search path until you fall out of the tree. That's only O of log n. And this is easy. This is easy. There's this test, which is easy. That's just a calculation. But this thing here, we got to go up and find a scapegoat and then rebuild the whole subtree rooted at u. That's going to take time, which is proportional to the size of u. It's as big as the subtree we have to rebuild. Okay. So I want to prove to you that over an entire sequence of add and remove operations, that we don't do, so the amortized cost is log n per operation, so that we don't do, over a sequence of m operations, we don't do more than log n. We don't do more than m log n work. Okay? So let me try and write that down a little bit more carefully. Here's the claim. Over any sequence of m add and remove operations, the total time spent in calls to rebuild is O of m log n. And why am I using a capital N here? Well, because now we're talking about a whole sequence of operations. Well, over a sequence of operations, the number of elements in the tree changes. Add and remove does that. So I will say this big N is equal to the maximum value of little n, the number of elements in the tree at any time. Okay. And that's just for convenience. We could be a bit more careful, and with a longer definition we could get something that makes more sense, but it certainly doesn't make sense to put a little n here, because little n is changing. Every time we add and remove something, the value of little n changes. All right, and the way that I'm going to do this is with something called a credit scheme. And here's how a credit scheme works. When I, well, here's the idea. Imagine that every time you come to class, I give you a token, okay? And that token, when you want to ask me a question, if you have a token, you can ask me a question and then give me the token. Okay? So every time you come to class, I give you one of these tokens. Anytime you have a question, you give me the token and ask me the question. And of course, as a lazy professor, I'm not interested in answering too many questions, so I want to make sure that this doesn't get out of hand. That's what the whole token system is for. So in a semester, you come to class maybe 24 times, which means in the whole semester, I give you 24 tokens. Now, over the course of the semester, if we're following this rule that you have to give me a token to ask a question, that means you won't ask me more than 24 questions in the whole semester. So that's similar to what amortized analysis is doing, right? I'm not asking how many questions did you ask today, how many questions did you ask last class, how many questions did you ask this. Maybe you saved up all 24 tokens and then just annoyed me to death during the last lecture with 24 questions, but still, at the end of that process, as long as we all follow the rules, you will not have asked me more than 24 questions. And the credit system for analyzing data structure like this is going to be the same thing. There's going to be times in the operation when I hand out tokens, and when the data structure does a rebuilding, it's going to have to pay for it with tokens that it has collected. And if it can pay, if it has enough tokens to pay for all its rebuilding, then I know that the total amount of rebuilding it did is not more than the number of tokens I gave it. All right. So it's got these tokens that it uses to pay for things, and it keeps them in two places. Okay? Here are the places. So there's a tree here. Now let me draw one with actual nodes. Okay, and the data structure collects tokens, which I'll draw as these little things. It collects them on its nodes, so it saves them up. Okay. So each node is collecting tokens. And there's another place off to the side where it's collecting tokens. It's saving them up over here on Q. Okay. So there's a token stash for Q, and then each node has its own little token stash. Okay. Good. All right, and it maintains a token invariant and it actually has two of them. The number of Q tokens saved up is at least Q minus N. So remember, you've got N, you've got 2N, Q is somewhere in between, and the number of tokens that it will have saved up is the difference between those two things. So it's always going to have at least that many of those Q tokens lying around. And the number of tokens on any node U is at least the size of U dot left minus the size of U dot right. Take the absolute value and subtract 1. So those are the two token invariants. And every time a rebuild happens, it's going to give me enough tokens to pay for that rebuilding. Okay. So that means if it rebuilds the whole, if it has to rebuild the whole tree, then it's going to give me something like N tokens. And if it has to rebuild, and let's even say, I don't know, we could say 3 here. Okay. If it rebuilds a subtree, it has to give me at least the number of tokens, which is the size of the subtree. All right. And it always has to maintain these things. So let's think about how that would work. So there's the tokens we only need to worry about using during 2 operations. So we look at a remove. For example, maybe we go and we remove this node. Okay. So I ask the data structure to remove this node, and I'm going to give it some tokens that it can use later for rebuilding. So what are the tokens that I'm going to give it? Well, look at the path from this node to the root, or the root to this node that I'm removing. I'll drop 3 tokens on each of those nodes on that path. And then this one's gone. Okay? So I drop 3 tokens on each of those nodes on that path. And I will also drop a token up here on Q. So let's see if that's enough. So there's 2 token invariants. One of them says that the number of Q tokens should be at least Q minus N. Well, when I remove, the value of N decreases, but the value of Q doesn't. So Q minus N increases by 1, but that's okay because I dropped the token here so that there would be a token there for this thing to have, right? So that's still going to be true afterwards because I left the token to make up for the fact that the value of N went down. The other thing says that for any node U, the number of tokens at U is at least 3 times the difference in size between the 2 subtrees. So here I was dropping 3 tokens on every node that I went down. So for example, so for example, here I did this. So so now, well, we don't see it here, but the point is, when I delete a node when I delete one node, look at what happens at the root. It has 2 subtrees, and they have possibly different sizes. And after I do the deletion, one of them has 1 less node, which means the difference in the sizes of those 2 subtrees has increased by at most 1. And that's okay, because even if the difference in size increased by 1, I left 3 tokens at the root to keep that okay. And the same thing along every node along this path. So if the difference in sizes increases by 1 because I'm deleting, then that's okay. Each thing gets 3 tokens that covers that. So this is still true. All right, so that's what happens during removal. And what about the rebuilding that happens during removal? Well, when do you need to rebuild? Well, you rebuild when Q is bigger than 2 times N. That's when you rebuild the whole tree. But if Q is bigger than 2 times N, that means Q minus N is N. So there's N tokens sitting up here. I'm rebuilding a tree of size N. So the data structure takes those N tokens that are saved in the Q pile, gives them to me to pay for rebuilding that tree of size N. Then it has no tokens left on the Q pile, but that's okay because the remove operation, when it does a rebuild, it finishes by setting Q equal to N. So now the difference between Q and N is 0, and so it doesn't need to have any tokens there anymore. It used them to pay for it, and now it doesn't need them anymore. Okay, so that's how you analyze remove. How do you analyze the add operation? Well, the add operation is going to do the same thing. When I add a node, maybe like to this node, I will, along every node along the path to that, I'll drop 3 tokens. Yeah, I can leave these here. And why drop those 3 tokens along every node on the path? Well, because when I add this thing, the size of each of the subtrees changes by 1, which means that the difference in size, like for this guy, now maybe the difference in size of his subtrees also increased by 1, so he should have 3 extra tokens available because of that. Okay, good. All right, and okay, so that's how you drop the tokens. You don't leave any tokens on Q because when we add, both N and Q increase, so their difference doesn't increase. So just drop the tokens here. And now look at what happens during a rebuild. So all we have to worry about now is if we go past the high water mark, we have to rebuild. It means we need to find a scapegoat and rebuild it. here's the picture of a scapegoat. Scapegoat has twice as many things on one side as it does on the other, right? If this is bigger than 2/3 the size, then this is less than 1/3 the size. Okay. So the difference between this and this is at least 1/3 the size, right? 2/3 minus 1/3 is 1/3. So, but hold on a minute. So that means the size, if u is a scapegoat, the size of u dot left minus the size of u dot right is bigger than the size of u divided by 3. You have more than 2/3 here, you have less than 1/3 here, so the difference is at least 1/3. So that's the difference in size, and this credit invariant here tells us that that's okay because the number of tokens that are sitting on u is actually 3 times that number. Okay. So then number of tokens at u is at least 3 times the difference in size, which is at least the size of u. So when I rebuild, u has enough tokens to pay for the whole cost of rebuilding this tree. U just takes its tokens and gives them to me. And why does it do that? Well, it does that because it doesn't need them anymore. In fact, nobody in this whole tree will need their tokens anymore because once they're rebuilt, they're in this perfectly balanced state, the difference in size between every 2 subtrees is at most 1. And if the difference in size is at most 1, then they don't need any tokens. Okay. So let's just recap very quickly. When I add something, I have to drop 3 times the number of tokens as the length of the search path. So that's 3 times this many tokens. When I remove something, I have to drop 3 times this many tokens plus 1 on u. Okay. So at each operation, I'm dropping at most 3 log base 3 halves of q tokens plus 2. And that's at most log base 3 halves of n, which is at most log base 3 halves of this capital N, the biggest N over any time. So over all those operations, I only dropped m times 3 log n tokens, plus another m for the ones on q, and those tokens are enough to pay for all the rebuilding. And so, so that tells me that just the way I explained it in terms of questions, this is how much money I gave out, how many tokens I gave out, and with those things, the data structure was able to pay for every rebuilding that it did, so the time that it spent rebuilding was not more than this. All right, so scapegoat trees give you amortized log n time for add, remove, and find, and the statement, the formal statement, you can look in the book, similar to what we saw for array stacks and array decks, all the other array-based data structures. It's that ignoring the cost of finding scapegoats and rebuilding, these run in log n time. Furthermore, over any sequence of m add and remove operations, the total time spent rebuilding is m log n. All right, so that's it for today. And that's it for this week. And you have a reading week next week. Use it wisely. Get some rest. Get refreshed. Do some work, but at a pace that you can do it relatively calmly now. We have instructions not to force you all to take exams immediately after reading week and not to make tons of assignments due immediately after reading week. Hopefully most of the professors have followed those instructions. If not, I'm sorry, I did. So that's all I can do. If you have any questions, you can give them to me in the next couple of minutes. Okay, so one question is, are the tokens actually stored in the data structure, or is this just a way of visualizing the amortized runtime? That's right. This is just a way of analyzing the data structure. The data structure itself, the implementation, you can look at the code. There's no notion of tokens. There's just these integers n and q and the binary search tree. This is just a way for us, when we're studying it, to understand why it's efficient. It's not quite as obvious as some of the other structures, because it's doing, this rebuilding doesn't happen all the time, only at the root. It's happening on little parts, and so we need some way to keep track of, okay, is this really efficient, or is there something that I'm not keeping count of? And the tokens are a nice way to do that, because precisely because of this picture, that when you're a scapegoat, it's because you've built up a pile of tokens that you can use to pay for getting out of it. So, you know, this is like, you know, political scapegoats, right? That's what they do. They do all kinds of bad stuff throughout their career. Then they get found out. They try to send them to jail, but they've been saving up favors from everyone, so they use those favors to get themselves out of jail, pay for their problems. Are scapegoat trees used because they're space efficient? That is one argument for them, but it's not a great one. They're used, again, because they're actually fairly simple, and in some cases they are more efficient. So why is that? So I said, look, scapegoat trees only really do rebuilding when they get out of balance, right? So when the height gets crazily out of balance, that's when they rebuild. And we saw already that if all you're doing, for instance, is adding things randomly to a binary search tree, then it probably never gets unbalanced anyway. So the height never will get big. So in that case, a scapegoat tree doesn't waste any time rebuilding. It doesn't do rotations, doesn't do anything. If the data that it's getting is really random, then it does great because it just doesn't bother to do anything. Nothing bad ever happens, so it never rebuilds. That's the main reason, is if someone is using them and the operations they're doing happen to give you a balanced binary search tree anyway, then scapegoat trees won't waste their time rebalancing unnecessarily. So old questions. There was, why not check the path to the max of the left subtree and also the path to the min of the right subtree, see which is longer, and use that as the replacer node. So that was about deletion. Well, if you check both paths, then you've already spent the time to look down both paths. Now you can write your code to do both of those in parallel, or in, you know, one step at a time in each path. But that means that you're still going to do twice as much work as the length of the shorter of the two paths. And so it's not really necessarily going to help you, because if the two paths have the same length, that means you did twice as much work as you needed. And so it just seems an extra complication. So the worst case for rebuild is always O of n. Yes, the time to rebuild is just the size of the tree that you're rebuilding. O of n in the worst case, but if you need to be more precise, it's the size of the subtree U. Okay. All right. So thanks for showing up today, and enjoy your break. Or let's not call it a break. Let's call it a reading week. Have fun.